Okay. All right, we'll make this work. All right. So welcome to Supercomputing in Plain English. This is episode 5, but chapter 4. Okay, so this is stupid compiler tricks. So we're going to learn all kinds of fun compiler stuff. As usual, this is an experiment. It will fail. Mute yourself.
No video in Twitch.
No video in Twitch. Yeah, that's so folks who are on Twitch or Wowza, you may need to move to YouTube or Zoom today. At least at the moment, I did not see the bridge from Zoom to those other things on Zoom. So I'm concerned that might not be live right now. Okay. We are encouraging people to use Zoom when they can. We're aware that not everybody can do that. If you're doing YouTube, you know how to get there. Just look for Supercomputing in Plain English. In Plain English is all one word. There's Twitch, Wowza, blah, blah, blah. The phone bridge is a last resort because we only have room for, I think it's 100 people on there. Mute yourself. Send questions to supercomputing in plain English, all one word, at gmail.com. Very exciting. Okay. I shifted us. So I got a request to do a talk, and it was at a non-PhD granting university for their essentially their computing day. And I love to do nice things for non-PhD granting institutions and for minority serving institutions. So I decided we would just push stuff off for an extra week. So we now have 2 weeks where there's no sessions. Happily, they're not right next to each other. And of course, thanks for helping to all the folks who are helping. This will fail. Things coming up. Okay, so now actual content. So we're really going to do 2 things. The bulk of the talk is actually going to be on dependency analysis. Dependencies are what control our ability to parallelize. So if we can discover the set of dependencies that we're dealing with, that helps us determine what can be parallelized and what cannot. And then time permitting, and I think this slide deck is like 98 slides or something, and we are not going to run for 2 hours. So whatever time we may have at the end, we will spend on things that you can do with the compiler and things compilers can do for you. But let's talk first about dependency analysis. So, and I mentioned this is understanding which parts of the code have to wait until other parts of the code are done. Yes, TV land question.
Brad Berkman says that he can't see the left edge of the screen on Zoom. Not significant on this slide, but will be in later ones.
Okay, left edge. Give me a second. We'll fix that. Just got to get it the right way here. Very careful. There we go. Is that better? I hope it's better. That's more centered. Okay. So if you know which things have to wait for other things to get done, then you can better parallelize your code. And we split that into 2 kinds of dependencies. So there are 2 kinds of people in the world. People who split the world into 2 kinds of people and people who don't. There are 2 kinds of dependencies. Control dependencies say which sets of instructions affect one another. Data dependencies say which pieces of data affect one another. Okay? And by the way, all of that is a little fuzzy, but we'll sort of use that as our category. So in any program, there's a flow of control. There's we do this, and then we do this, and then we do this. And we might skip over a bit of it and come over here and do these. We might come back up here and do more of this, and we come back down. No, we'll do it again, and so on and so forth. Okay? So we call that the flow of control. And there's lots of different constructs in our programs that affect the flow of control. And those constructs also affect our ability to parallelize. Okay. So let's start. And we've got, I think for all of these, I have both a Fortran version and a C version. So I'll show you one or the other, sometimes both. But they're usually similar enough that this won't be terribly confusing. So here's the Fortran 90 version. So branch dependency, so I've got y is assigned 7, and then I've got an if on x, and I would change the value of y based on the value of x. And then z is dependent on y, so it then in turn is dependent on this if block. So if is a kind of branching. If you do switch, that's a kind of branching. Please don't do go to, but that is also a kind of branching. Okay. So in the event that x is small, that is that condition evaluates to true, then we're going to change the value of y, which will then in turn change the value of z. So what I can't do is I can't be calculating z while I'm changing the value of y. Those things can't happen at the same time. So I can't parallelize that part of the code. Okay. So there's the C version. A loop carried dependency. So this is a wonderful way to inhibit parallelism inside a loop. For example, this would inhibit pipelining. So I can't do iteration 3 until I have the value from iteration 2. But I can't do iteration 2 until I have the value. I can't say from iteration 1 because you notice the loop starts at 2. But I can't calculate the value of a of 2 until I already have the value of a of 1. And so on and so on. So that's going to inhibit my ability to parallelize that loop because each iteration is going to have to wait for the previous iteration to get done. So this is called a loop carried dependency, a dependency that's carried by the loop. There's no way for me to execute a particular index until I've completed executing the index code. So there's the C version. So why does that matter? Well, as we mentioned last time, we have wonderful things like pipelining and super pipelining and vectorization, all of which assume and require that the different iterations of the loop don't care about the other iterations. So the iteration for index 12 should not care about index 95. And what we see in a loop carried dependency is that index 12 depends on index 11, but to make that worse, index 11 depends on index 10, and index 10 depends on index 9, and all the way down to index 1 or 0, depending on whether we're doing Fortran or C, right? So everything depends on everything else. That means that we can't pipeline, we can't vectorize, and so that loop is going to run much slower than if we could do things like vectorizing. Okay, so then this raises the question. Is this a loop carried dependency, or is this a branch dependency? So how many of you vote it's a loop carried dependency? An iteration depends on a previous iteration. And how many of you vote that it's a branch dependency? So it depends on the branch, but not on the branch in a different iteration. Yeah. So that's what we see here. So everything is the same index. So we're not dependent on a previous index. We are, however, dependent on what this particular expression evaluates to. And if you're a C or C++ or Java programmer, / equal in Fortran is exclamation equal in C. So good. So get that one well worked out. All right. A call dependency. So I have to stop what I'm doing and go somewhere else, namely to whatever that function is, before I can continue on. Okay. Now, in theory, if you have in this particular case, if you have a smart compiler, that smart compiler will go, oh, well, that call to that function is not going to need what's going on here. So I could be doing this at the same time as either when I'm assigning x is assigned 5, or maybe during the call, I could be doing it. But the difficulty with that is, what if z has a scope, is visible to the program outside of whatever function this is happening in, whatever routine this is happening in? What if it's, here's the C version, what if my function can see z? Now can I call my function? If my function can see z, can I guarantee that my function won't look at z? Or even try to change z? So unless I can guarantee that, which means I need to be able to look at my function at the same time. This is sometimes known as inter-procedural optimization. I have to go look at the text of my function, and not just the text of it, but the whole context of it. Because, okay, so let's use a dirty word. If this were in Fortran, it could be that Z might live in a common block. How many of you know what a common block is? Okay, they are poison. Stop using them. Or it could be that Z lives in a module that my function can see. Or if I'm in C, it could be that Z is a global variable that my function can see, right? So the compiler then has to go look at the whole context of what's going on in order to be smart enough to figure out, can I afford to have Z is assigned 22 before I come back from my function? Now, there are compilers, in fact, most modern compilers are smart enough to do that, but they don't do it by default because it takes a lot of extra compile time to do inter-procedural optimization. All right, an IO dependency. This is the same sort of principle, right? So don't start additional calculations until you're done doing the IO, because you never know what might get messed up by that. By the way, could it be that D and X live in the same location in memory? Can that happen? Let's be Fortran for a minute. Okay, how many of us here in the room are Fortran people? Okay, so I call a function or a subroutine, and I pass it, I'm supposed to pass it 2 arguments. So inside that subroutine, the arguments are named A and B. And let's say they're both integers. Okay. Can I, in my call to the function, pass the same variable twice? Can I say, my routine, open parenthesis, x comma x, close parenthesis? Is that permitted by the compiler? The compiler will let me do it. But then in the subroutine where I have A and B as the dummy arguments, the formal arguments that x and x correspond to, do A and B now live in the same address? They totally do. So D might be x, or worse, y might be x. So can I change the value of y while x is being output? So think of this as a special case of the call dependency, because after all, what really happens under the covers in any programming language, under the covers, I/O is handled by some kind of procedure call. Right? There's some place somewhere in the code that's built into the compiler that does all of this, and the compiler is smart enough to set up that call internally, and that's pretty much true for any language. Okay, so there's my I/O dependency. Now, I had mentioned, I think it was a couple of weeks ago, this concept of a reduction. Anybody remember what a reduction is?
Some kind of sauce.
No, not a sauce. Although, interestingly, so what makes a reduction sauce a reduction as opposed to just a sauce?
I don't know.
So I believe, anybody here know much about cooking?
Evaporation.
Yes, you evaporate some of the liquid. So you take something that has a lot of liquid and you reduce it down to a lot less liquid. Is that correct? Okay, so the same principle with a reduction in computing. A reduction is you take a lot of, for example, numbers. Let's just say more generally a lot of data, and you reduce it down to a few data or perhaps even just one. So in this case, I'm taking a giant array of 1 billion values, and I'm adding them together to get a single sum for that 1 billion values. So I went from 1 billion pieces of data to 1, right? And in real life, the place where I would, for example, do this would be to calculate a mean, because the mean is just the sum divided by how many there are, right? So the next statement here could be array mean is assigned array sum divided by length. Right? That's the thing you would typically do. So a reduction doesn't create a dependency. Okay? And the reason that a reduction doesn't create a dependency is because these reduction operations have the wonderful property of being commutative. So it doesn't matter what order you do things. And if it doesn't matter what order you do things, then one of the orders that you can do things is at the same time. It turns out at the same time is itself an order. Okay. So reductions are very, very common. We do them all the time in computing. So they've worked really hard to get them to run fast. Right? And in fact, it turns out they are super duper fast. Much faster than, for example, doing pairwise adds of corresponding elements of two different arrays. The reason being, when you're doing so if you have C of I is assigned to A of I plus B of I, right, inside a big loop, right? You're going to do a billion of those. Well, every single iteration of that loop is 3 memory references, whereas here every iteration of the loop is only 1 memory reference because array sum is being used over and over, so it's going to live in a register until we're done. And so we're just getting one element of, we're getting an element from one array, not elements from 3 different arrays. So this is actually typically much faster than some kind of pairwise operation because there's so much less memory to deal with. Okay? All right. Oh, and there's the same thing in C. All right, now data dependency. All right, so I stole this from whichever book, and there's a reference to it at the end of the slides. A data dependence occurs when an instruction is dependent on data from a previous instruction and therefore cannot be moved to be in front of, ahead of, before the earlier instruction or executed in parallel with it. Okay? So if I've got A is going to be assigned this whole mess, and then B is assigned A times something, then I can't calculate B until I finish calculating A. Now, that's kind of that's half true, because there's a cheat I could do. The cheat I could do is a terrible idea, but I can do it, which is I could calculate this ugly expression twice in a row. Once to get A, and once substituting this whole thing for A in the second assignment statement. I could do that, but it's going to be a lot of extra work. Now, in this specific case, cosine is going to take a long time to calculate. Cosine, typically you're looking at an excess of 100 cycles to calculate a cosine, whereas the incremental cost for doing an addition or a multiply is going to be typically on the order of a cycle, right? So it's going to take much longer to do this. So here, it totally would not be worth it, right? Because the amount of time you're going to wait after this is going to be minimal. But if this was just x plus y, maybe it would be worth doing. Maybe it would be worth doing A is assigned x plus y, and B is assigned the quantity x plus y times C at the same time, because that might get you done faster. Right? By the way, how do you decide which one to do? How do you know which one's going to be faster? So the answer is you don't. And in fact, it's the compiler making these decisions, but not just the compiler, because then when you're running at runtime, most modern CPUs participate in the decision making about what to do when. It's not just the executable. There are CPU families where the compiler does all the thinking about the instruction level parallelism. But most contemporary CPUs, that's not true. Most contemporary CPUs, it's a combination of the compiler and the hardware working together. Well, the executable and the hardware at runtime, the compiler to create the executable. Does that make sense? All right, output dependency. Now, I'm going to vote this is a terrible name, because I would like, in real life, to reserve the word output to mean put out somewhere. So, for example, to display on a screen. So this picture here in front of us is the output of PowerPoint, right? I like to reserve the word output to mean only that. And then I'd like to reserve the word print to mean output to paper. However, I'm apparently the only one who believes that, and we can tell this because most programming languages have a command that has print in it, like print in Fortran or printf in C. In Java, I think it's called write line, so that's slightly different, but still I'm not crazy about that usage, but okay. So having said all of that, so I'm not crazy about the use of the word output here, because here it does not mean put out on the screen or on paper. Here, output means the result of one calculation which can then be used as, and I'm putting it in scare quotes, input into the next calculation. I don't like that at all. I'm not fond of that usage, but it is a common usage that we're stuck with. So an output dependency means this calculation has to wait until that calculation is done, because it's going to use the result of that calculation to do this calculation. But to make that worse, here x is assigned a brand spanking new value at the end. And the result is that I can't wait for this, I can't do this and this at the same time. And I certainly can't do the first two at the same time, obviously. I can't do the second two at the same time. Now, by the way, again, a smart compiler, and most compilers today are quite smart. A smart compiler will notice this, and it will say, aha, I know what to do. I will create a hidden secret temporary variable, let's call it xtemp, that I will use for the first two statements here. And then I will calculate this at the same time as I'm doing xtemp. Because after all, the old value of x is going to get clobbered by this new calculation right away. Now, I've cheated, right? Because I've showed you a super simplified example where I use it and then I immediately change it. In real life, we're not always that lucky. It might be I calculate it, other stuff happens. I use it, other stuff happens, and then I change it, right? That's the much more common scenario. So there, I have to be even more watchful, right? So the compiler has to keep track of all this stuff all the time, all the way through whatever that procedure is, that function, whatever it is. All the time, it's tracking this stuff. So you may have that output dependency, but it may not be obvious that it's there. Okay. All right. So why does all this matter? Why do we care about the order? Because to get the right answer, you have to do things in the right order. And if you come across a situation where there's a dependency, then that inhibits your ability to parallelize. And if you can't parallelize, your code runs slow. Okay. So we got to be careful about that. All right, so now here's a bunch of loops that are all very similar in that I've got, I'm looping over a large number of elements in some number of arrays, and I've got destination of whatever index is the sum of a couple of elements, okay? So at the very top, I've got destination of index is assigned destination of index minus 1 plus destination of index. By the way, I've got index for the destination and then index minus 1 for the first operand for the, what is this, the addend, and index for the augend, the second operand. Okay, these are all doing addition. So notice, if it's dest of I is dest of I minus 1 plus dest of I, what do I have there? What's that evil kind of dependency that we hate? That's the loop carry dependency. And so right away, that's going to inhibit pipelining. It's going to inhibit vectorization, right? I'm going to completely not be able to parallelize that loop. Okay, so here's another variation on this theme. Dest of I is dest of I minus 1 plus source of I, source 2 of I. Okay, well, that didn't eliminate the loop carry dependency. I've still got my loop carry dependency there. Now, on the other hand, if this one, if the one that has index minus 1 is a different variable, in this case it's source 1, for this middle one, okay, then I can pipeline, I can vectorize, because I no longer have a loop carry dependency. The loop carry dependency has to be in the same array, right? Because otherwise it's not a dependency. Okay, well, not loop carry anyway. So here I've got source 1 and source 1, and here I've got source 1 and source 2. And none of these, the last three, do not have loop carry dependency. So they will run super fast, whereas the first two will not run as fast because we cannot parallelize them. Now, having said that, I need to balance that by saying this one in particular, the last one, I've got 3 different arrays that I'm drawing in from RAM into cache. The first one, I've only got 1 array. Right? So we're balancing, on the one hand, parallelizing via pipelining or vectorization against, and actually probably both, against how much RAM we're having to access. So that's going to affect the performance. Okay? So I already said that. So here's a picture of that. So these are the 5. I've stacked them horizontally instead of vertically, but you can get the idea. And these are on different CPU flavors. I think they're all using the same compiler. I think they all use GCC, but never mind. Okay, so over here we can see, right, with these different CPU types, we can see that, for example, this, here we go. They're stacked in the opposite direction. So here we have pretty poor performance over here. But on the other hand, over here where we have more arrays, that also causes poor performance. So the middle ground of few arrays, but no loop carry dependency is where we're going to get the best performance. Does that make sense? So we, on the extreme end of loop carry dependency, but only one array, we get poor performance. On the extreme version of no loop carry dependency, but 3 arrays, we get poor performance. Okay. All right, now we can do some stupid compiler tricks. Are you excited?
Yeah.
Okay. So we'll do some tricks that compilers play and some tricks that you can play with your compiler. So here's the thing. Compilers have been around for a very long time. The oldest, well, more or less the oldest high-level programming language. The first programming language, or at least almost the first programming language that was not assembly language, that was not CPU specific, was the very first version of Fortran, which I think was 1958 or 59. So we're looking at a 60-year span now. C came out in 69 or 70, depending on when you want to count it. So it's actually getting almost to 50 years. C++ came out, I think, in the early 80s. So we're at 30 plus years. And on top of that, the people who wrote C++ compilers, they were able to take advantage of what was learned developing C compilers as well. So the folks who've been spending now 40, 50, 60 years developing these compilers, they've gotten pretty good at it. That's the key thing here. Okay, so what do compilers do for us? Okay, so I got a list of them here. We're going to walk through them. Not every compiler does every one of these optimizations, but every one of these optimizations is quite popular. Okay. Copy propagation. You can see that's a tongue twister, right? X is assigned Y and Z is assigned 1 plus X. So that's got an output dependency, right? I have to wait until I've finished with X assigned Y before I can assign anything to Z. But if I'm clever as a compiler, I will notice that I can take the Y from the first one and propagate it down to the second one. And now these two assignment statements can happen at the same time. Now I can do them in parallel. So I've eliminated the waiting around time. I don't have to wait for the first one before I get started on the second one. So that's very convenient. Okay, and there's the C version. Constant folding. So notice in the before case, the addend is a constant, and the augend is a constant. So what can I say about the sum? Can I know the value of the variable named sum before I run the program? Can the compiler determine the value of sum? So what is the value of sum? 300. What did you do? You added 100 and 200, right? Okay. Would you have to do that at runtime, or as the compiler, could you notice that? Could you say, oh, that's a constant, that's a constant. I'm adding 2 constants together. So can I go ahead and add that at compile time?
As long as we're not changing the value.
Well, sure. I mean, if later on we change the value of something, that's fine. But here in the code as written, and as long as nothing changed above it, I agree. But in the code as written, right, I can pre-calculate sum at compile time. Oop. So now do I have to spend time at runtime calculating that? No, it's already done for me. This actually can be really super valuable if you've got lots and lots of these, like a big array that you're doing this sort of stuff with. But if all of the terms of a calculation are constants, so they're known at compile time, then the compiler can do the calculation at compile time, and then that doesn't have to happen at runtime. That's just the C version. Okay, dead code removal. So dead code is code that is in the source file, but is guaranteed never to actually be executed. Okay? So the stop in Fortran, that's like the exit statement in C. Okay? So I'll show you both versions there so you get the idea. So this print statement here, will it ever be executed? No, because we get to a stop. Stop means stop executing. It means shut the program down. We get to, in the C version, an exit statement. So we'll never, ever actually execute that. If we're never going to execute it, does the compiler need to compile it? No, it's just going to take up space in the executable. So the compiler will throw that away. It says, oh, this code is dead. I'm never going to execute it. It's impossible to execute that code, therefore get rid of it. So that's a pretty good thing to do. And one of the reasons, by the way, that that's a good thing to do, so we remember about our caches that, we have L3 cache, and L2 cache, and L1 cache. Most CPUs today have the L1 cache split into two chunks. There's a data chunk and an instruction chunk. And so if you eliminate dead code, that means that the instructions that you are working on are more compact, fit in fewer bytes, therefore are more likely to be able to fit in your L1 instruction cache. So making the executable smaller is a win, except when it isn't. But in the case of dead code, it's pretty much always a win. All right, strength reduction. So I mentioned last week that the most expensive calculation to do is x to the y power, where x and y are both reals. Okay? That's incredibly expensive to do. And on virtually every CPU flavor today, it's the most expensive calculation that's built into the hardware. Okay? But if you carefully notice that the power you're raising to is a constant, and if that constant is an integer, by the way, not an integer in data type, I mean an integer mathematically, right? Because 2.0 is a real, it's a floating point number. So it's not an integer in the data type sense, or for the C and C++ and Java folks, it's not an int. Right? But if you notice that its value mathematically is an integer, then the cheaper, much cheaper way to do the calculation is to multiply. Okay? So instead of doing y to the power of 2, the compiler will go, oh, y to the power of 2. I'm raising to an integer power. I'm just going to multiply. Because multiplying takes, once you get going, takes like 1 cycle per multiply. Whereas raising to the power takes, not kidding, hundreds of cycles. So I'm going to have a huge speed up by noticing that. Likewise, dividing. Now, here it doesn't matter whether it's an integer or not. In fact, arguably, it can be better if it isn't. But so dividing something by 2 is the same as multiplying it by 0.5. And which is cheaper to do? Which is cheaper to calculate? Multiply is cheaper. So divides, typically we were seeing was what, like 7 cycles? And a multiply, once you get going, multiplies are 1 cycle. So we get a significant speed up by doing what's called strength reduction, where here the word strength, and again, I'm not crazy about this use of the word, but this is the word we're stuck with. Here the word strength means how time-consuming it is to calculate it, which is a terrible, terrible usage of the word strength, but there it is. We're stuck with that. Okay. All right. So here's another trick. Okay, I've got 2 assignment statements. Both of them have the sub-expression a divided by b. And remember, a divided by b is expensive to calculate. So how about when I calculate a divided by b in the first one, in the first assignment statement, how about I notice that a divided by b is showing up in the second one, and I hang on to it so that I don't have to recalculate it. Okay, so maybe I'll leave it in a register. So then when it comes time to do the second calculation, when I'm doing the assignment statement for E, I say, oh, I still have that. I'll just plug it in. And that'll save me some time. Now, there's a hidden assumption here, which is that I've got somewhere to put it that's cheap to get to. Because after all, it might very well be, and in fact on most CPUs today it is, it might very well be more expensive to go get something from RAM than it is to divide. So it's only worth doing if I can put it, for example, in a register or maybe in L1 cache. Probably I'm going to put it in a register in the following sense. At compile time, I can keep it in that register and not clobber it. Whereas with cache, that's harder to guarantee. Of course, the problem then is if I've got a lot of that sort of thing going on, and in real life I do. If I have a lot of that sort of thing going on, I might run out of registers. Because remember, we don't have much in the way of registers. So we're going to be really careful about how we do this. By the way, all of these things, they are never guaranteed to make it faster. They're also never guaranteed to not make it faster. So it's kind of, we are hopeful that it will work out well. Okay. Variable renaming, and this was sort of what I was just talking about. So I can cheat my way out of an output dependency. So here's an output dependency. I can cheat my way to fun and profit by not using X twice. Because after all, I know that this X is going to clobber this X. So if I set up a temporary variable, here I've named it X0, right? I could name it anything, X10, whatever. Use that, and then calculate this X. Now notice, I still do have a dependency, a data dependency between these two. But this one now actually can happen whenever I want. Assuming there isn't some other weird dependency going on, which there might be. Okay. All right, so that's variable renaming. Now let's talk about some loop optimizations. Those were the sort of scalar optimizations. Now let's get to our loop optimizations. They get even weirder. Isn't this fun? Weird stuff that compilers do to make your code faster that you didn't even know about, that you never dreamed was happening. Cool stuff. All right, loop invariant code. What that means is code that doesn't vary inside the loop. So here is E is assigned G of N inside a loop where we're going I from 1 to N. Right, here's the C version for you C folks. Okay, we're sticking on the Fortran side. Okay. So what I can do is I can take this assignment statement. I mean, first of all, I don't need to do that over and over, do I? It's not going to change the value. So I can take this assignment and just stick it afterwards. That's called syncing. Okay? And here, this sub-expression doesn't need to be calculated a million times. We just calculate it once, put it in temporary. Perhaps it's even a register. Okay? So temporary gets that expression. Do the loop and use the temporary over and over. And then take that assignment statement that's not changing from iteration to iteration. Just stick it at the end. So a smart compiler, and nowadays they're pretty much all pretty smart. Most compilers today will just automatically do that. They're pretty clever. So they hoist or sync the loop invariant code. Okay. Oh, this is fun. Unswitching. And here we get weird. Are we ready for weird? Okay. Yes, question from TV Land.
For repeated expressions, a few slides back,
Yes.
what if A or B change? Because
Right, okay. So what if in the common subexpression elimination, what if the value of A or B were to change between this statement and this statement? Then you couldn't do the common subexpression elimination because it's absolutely true that they would no longer be the same subexpression. That is, they wouldn't be operating on the same value. So common subexpression elimination, that term refers only to the case when the values of the things in the common subexpression don't change between the different statements that use the common subexpression. And the trick is that the compiler has to watch every expression like a hawk to make sure that there aren't any dependencies like that. So when the compiler is working through some routine, a subroutine, a function, whatever, a method if you're in C++ or Java, when the compiler is working through that routine, it's looking at everything in that routine to try and discover every single possible dependency. And it's going to use the information about which things depend on what to make decisions about what of these tricks it can do. So it won't do a trick if that trick is going to give it the wrong answer. Now, I just lied to you. Compilers do actually do tricks that will give you the wrong answer. This is sometimes referred to as aggressive optimization. They will do unsafe changes to your code that can give you the wrong answer. I mentioned this last time. And the trade-off is your code will run faster because you're optimizing more aggressively, but you risk getting the wrong answer. And the only solution I know to that problem is you have to test the code at each level of optimization, from no optimization on up, and compare the results at each level to see whether they are at least pretty close. They almost certainly will not be identical because floating point calculations are approximate. I got a whole screed about that we won't have time to get into today. But if it's close enough from your perspective, then you can do that kind of aggressive optimization. If it's too far away, then you have to back off from that amount of aggressive optimization and do something gentler that is less likely to cause harm. Yes?
Is there any chance that those mistakes are affected by the input file? Or
Can those mistakes be magnified by the values of the input? Oh, yes, they can. Yeah, that's a huge problem. So to give you a very simple example. So what if I'm going to multiply or divide by a really small number, right? We're going to get to the limit, the edges of what the floating point approximation can properly handle. And so sometimes what you'll get is instead of dividing by 0, which mathematically is what should be happening in some cases, you'll divide by 10 to the minus 36, which feels like 0. But when you divide by it, suddenly your numbers get really, really big because you're dividing by something that's really, really small, as opposed to dividing by 0, which should cause your code to crash. Right? Which it's much better if your code crashes in a very obvious way, as opposed to being subtly wrong, and then the wrongness magnifies as you do more and more iterations of whatever it is you're doing. So that is absolutely a risk. Yes. And there is no solution to that problem. There's just being careful. Okay, now, in order for this next bit, so we can do this one, I think, pretty straightforwardly. So let's take a look. We've got a doubly nested loop for a 2-dimensional array. Right? So we're doing some calculation. It doesn't really matter what it is. But we've got this 1D array. We've got this 1D array here. And then we've got a 2D array there. Okay, so maybe it's a matrix and a couple of vectors. Right? Or whatever it is. And inside the inner loop, I've got an if. But my if is only dependent on the outer loop. Well, in that case, do I need to do it again? 10 minutes? 5? How much? 15? 15 minutes, okay. So I'm just going to go till I run out of time, basically, because I got more slides than I got time here. So in the event that the if only depends on the outer index, the index of the outer loop, then what I could do is I could hoist that if outside of the inner loop. So it's inside the outer loop, but outside of the inner loop. Yes, question?
Which is faster? Let the compiler identify and remove common sub-expressions or explicitly remove it ourselves?
Oh, is it better to do it yourself by hand, or is it better to let the compiler do it? What do you imagine the answer to that question would be?
Do it by hand.
Okay, so we got some do it yourself, and you've got compiler. Good, so you're fighting it out. What do you say? Okay, so I got 2 votes for compiler and 2 votes for do it yourself. And the average answer is correct. That is, there is no good answer to that question. Sometimes the compiler will do it well. Sometimes it's better to do it by hand. And it is literally impossible to know which one will be the correct answer until you've tried it. And trying it won't solve the problem either. Because if I compile the code today on this hardware with this version of the operating system with this version of the compiler, right? And I run it today, am I guaranteed the same performance when I run it tomorrow? Why not?
Better CPUs.
Okay, so tomorrow there could be a change of circumstances, right? I probably don't have new CPUs tomorrow because then we go to all the trouble of like recompiling it on the new machine. But I might have, there might have been a patch to the operating system where I'm using a slightly different version of the operating system today than I did yesterday, right? Or they might have upgraded the compiler and I'm using a slightly different version of the compiler today than I did yesterday. Whatever benchmarking I did yesterday is now thrown out the window, right? Now, in practice, it'll probably be pretty similar, probably, but not guaranteed. But let me make it worse. So who else is running on the machine today compared to yesterday can totally change my performance. So for example, I submit my code to the batch system and I submit it non-exclusive because I want to make sure to pack as many of these. I've got a lot of these to run. I'm going to run 1,000 jobs, right? All of them single core jobs. I've got 1,000 of these to run. I'm not going to say, give me the whole node to myself for this one single core job. I'm going to say, put as many of these jobs on this node as there are CPU cores. So that's called running in non-exclusive mode. Okay? And some of you have gotten hate mail from us about you either should or should not be using exclusive mode for certain kinds of jobs. Okay. How many of you have gotten that hate mail? Nobody? Really? All right. Oh, okay. So Chow has gotten that hate mail. Good. All right. So this is normal, right? We're trying to help you get better outcomes than everybody else as well. Okay. So I don't want to run in exclusive mode. So today, when I run my jobs, some of my jobs are running on the same node as some of Chow's jobs, because she's also running in non-exclusive mode, right? And my jobs are very memory intensive. So they're doing lots of movement of data between RAM and CPU. And Chow's jobs are not. Chow's jobs are very CPU intensive. They're making very good use of the cache. And so she's barely using stuff, she's barely moving data between RAM and CPU at all, right? So my jobs are going to have more RAM bandwidth available to them, so they're going to run pretty fast. But tomorrow, Jim's going to have a bunch of jobs on there, and Jim's jobs are going to be memory intensive, unlike Chow's, which are all CPU intensive. So now when my job lands on a particular node and Jim's job is there too, we're fighting for that memory bandwidth. So the jobs aren't going to, so tomorrow's jobs will not run for me at the same speed as today. So my joke is, the speed of the run depends on the hardware, the operating system, the compiler, the code itself, the day of the week, and the color of your socks. So if you wore blue socks yesterday and you wear pink socks today, you're going to get a different performance. I can virtually guarantee that the performance will be different. I admit it will not literally be because of the color of your socks, but there's so many factors that feed into this that there are no good decisions. There's the best we can do. And by the way, it beautifully reflects real life. In real life, can you make the right decision? There's no way to make the right decision. You make the best decisions you can with the information you have, and you hope, right? And sometimes the hope pans out, and sometimes not. The other week, I was getting myself some ice cream, and it was in a nice, beautiful glass bowl, and I bobbled the bowl, and it cracked on the tile floor. And I didn't get ice cream, and I had to clean up a bunch of glass. That's life. Okay, anyway, so that was a long way to go to get here. So because my if condition only depends on the outer loop's index, then I can pull it out of the inner loop. So now it's only inside the outer loop, not the inner loop. But what that does mean is I've got to take the actual loop part of the loop, the in this case do statement, or in C, C++, or Java, it would be the for statement. I've got to duplicate it in the else clause. So I got to be careful that I do that correctly, but I can do that. And so that means instead of doing n squared evaluations of that condition, I can just do n evaluations of that condition. So if n is 1,000,000, I've just reduced that part of it, the number of evaluations of that condition, by a factor of 1,000,000. That's a pretty big win.
Is it more efficient?
Yeah, absolutely, right? And when I say absolutely, it depends. It always depends. But in principle, that's going to be much more efficient because I'm only going to do this evaluation n times instead of n squared times. All right, iteration peeling. When I've got special cases, sometimes I'll end up with a special case that I've got inside the loop because that was the convenient way to write it, but it's very special and I should do something different. So how many of you have done a numerical method involving, what is it, Dirichlet boundary conditions, where you just copy the, does anybody have a fancy, are you all bioscientists or something? Bioscience, have you done Dirichlet? Somebody in TV land has done Dirichlet?
Well, they've got a question.
Mm-hmm.
Victoria asked, does this method only work if the exceptions are for the beginning and end of the loop?
No, if you've got an exception in the middle, that'll work too, but then what you have to do is you have to have two versions of the loop, the stuff before the exception and the stuff after the exception. That's a great question. Okay. So here I've done, I think this is the Dirichlet, what's the other one? I think it starts with a G. That's similar to that, but not identical. Anyway, don't worry about it. So I've got a special case on both ends of the array. So what I can do is I can write the code with the special case inside the loop, or I can pull out, I can peel off the special case iterations and just have the regular stuff inside the loop. And that'll save me the trouble of checking which loop iteration am I in every iteration of the loop. So I've eliminated doing the if, but I still have the same outcomes. Okay. Index set splitting. So this is the more general version of iteration peeling. So what I'm going to do is I say, oh, okay, so some iterations of the loop, I'm going to do this stuff. Some iterations of the loop, I'm going to do that stuff. In this particular case, it's all iterations of the loop, I'll do this, and some of them I'll do this other thing. Now, there's a couple ways I could do this. One is, I could, in this particular case, there isn't really a dependency between D, well, D could be done entirely afterwards. I could march through the entire array twice. Problem with that is, that'd be a lot of extra moving of RAM into the CPU cache, right? I don't want to do that. That's very time consuming. So instead what I'm going to do is I'm going to split the indices of the loop into two subsets. The subset where I only do this, and the subset where I do both. That also eliminates having to do the if at all. Right? Now I don't have to do the if, because now I'm guaranteeing that I'm doing the stuff that would happen. Now, okay, so this one is hard. And the reason it's hard is because in order to talk about this, we have to talk about how 2D arrays are laid out in memory. And the problem with that is it depends on whether you're doing Fortran or not Fortran. So C, C++, and Java all do the same thing, and Fortran does the opposite. So I'm going to talk about Fortran, and then I'll talk about C, C++, and Java. So in Fortran, if I have a 2D array, by the way, in real life, memory is not 2D. In real life, memory is one-dimensional. Every byte in RAM has a single address, and that address is an integer. So it's like having a street that everybody in the world lives on, and we all live at an integer address. So there's a little like 125 and a half. There's nothing like that. So it's just 0, 1, 2, 3, and so on until we get to 7 million. So this is a street for every man, woman, and child in the world. Each one of us has our own house, and the numbering is consecutive. So in other words, yes, 10 minutes, 5 minutes? Wow, time passes. All right, I'll go a little over, but I don't want to go too far over. Okay, so when we get to a 2D array, we're going to be putting that 2D array in 1D memory. So the way we cheat that is we take a row of the array, and we put all of the columns of that row next to each other in memory, and then the next row of the array, and then the next row. Let me try and do this all the way. So here's the first row of the array, and the second row. Oh wow, it turned on the light over there. And the third row of the array. Can you go set that back on 3? That's going to wash this out. Okay. So far so good. So in Fortran, the I values are next to each other in memory. In other words, if ij is here, index ij of this 2D array is here, then index I plus 1j is here, index I plus 2j is here, and so on. And eventually we'll get to index 1, comma, j plus 1. Okay, that's Fortran. C does the exact opposite. So in C, ij is here, and ij plus 1 is here, and ij plus 2 is here, and eventually we get to I plus 1, 0. It's right over here. So the i's jump around in C, C++, and Java. In Fortran, the i's are right next to each other. Does that make sense? That's good. So what we want to do is we want to make sure that the outer and inner loop go in the right order, so that we're running the loop as quickly as possible by marching from one end of the memory to the other, instead of jumping, right? Because we would go ij plus 1, ij plus 2, and eventually we'd have to come back to do I plus 1j, I plus 1j plus 1, I plus 1j plus 2. That's, you can see that's terribly inefficient, right? Because we're drawing stuff into cache from RAM and then clobbering it with something else. So what we do is we just swap the order of the loops. So we put j, in the case of Fortran, we put j on the outside and I on the inside. Now we're marching from one end to the other. So we got a lot better performance because we're reusing the cache line that we drew in. Okay? In Fortran, in C, C++, and Java, the order is the opposite, but the principle is the same. So we don't want j on the outside, we want I on the outside, because j is the thing that's next to each other. All right. Oh, this is a fun one. Unrolling. This is so weird. But this is really true. This is actually how it's done. Okay, so I've got a regular old loop where here I'm just doing a of I is assigned a of I plus b of I. So I'm increasing each value of a by the corresponding value of b. And by the way, it could be anything. It doesn't matter what's in that loop. It could be anything. What I'm going to do, under the covers, hidden behind the curtain, I'm actually going to jump by some several at a time. And inside the loop, I'm going to do that many different indices at the same time. That'll have a couple of happy effects. One, I will have to trip through the loop fewer times. Because every time I come down here and I have to branch back up here, that costs me some time. So by reducing how many of those, I don't have to pay that time cost very often, or at least less often. The second thing, it turns out it makes it a lot easier for the compiler to vectorize that kind of stuff, particularly if the number of iterations that you unroll to is a multiple of the size of the array. Sorry, the size of the vectors. So this gets me speed up, but it's really goofy. Now, it turns out for a one-dimensional array, you should never do this by hand. Let the compiler do it for you. If you have a two-dimensional array, it's much harder to predict whether it's a good idea to do it by hand or not. In fact, basically impossible. So, all right, I said all that. Okay, now, this is the scary part. Fusion. So remember last week we were talking about everything that you learned in your Introduction to Programming course about how to write code is the exact wrong thing to do if you want the code to run fast. That is, when we learned, how many of you took a formal programming course like for a grade? Ooh, very few. Surely you took one. No? Yes? Okay. So when you took that course for grade, they taught you keep your data small and keep your routines small. Subroutines, functions, methods, whatever they're called in that language. Keep them down to like 10 lines a piece. Certainly no more than 100, but ideally 10 lines or fewer for a particular routine. To get performance, you don't want to do that. To get performance, you want to have big chunks of data, giant, huge arrays. And you want the operations that you do on them to be very big and have lots of stuff in them, because that'll make it easier for the compiler to optimize. And you'll get a lot more reuse of whatever you've already drawn into cache, which is a win. Okay. So here's 3 different loops. A of I is assigned to B of I plus 1, C of I is assigned to A of I divided by 2, and D of I is 1 over C of I. Okay? So, since they're all looping over the same indices, I could just go ahead and fuse them together into one big loop. And look at the win, right? So now A of I gets reused and C of I gets reused. So I'm taking fewer marches through the memory where those arrays live. So that's a win, right? So far so good. But then we have this other concept called fission. And by the way, notice I cheated this by using the exact same thing, and I just flipped top and bottom before and after. Okay, look, there's 3 different things going on inside that loop. So I could split it into 3 different loops. Okay, why would that be good? Why would I want to do that? Because then, if these are really big arrays, then I'm doing less clobbering of things that I've already drawn from RAM into cache, right? Because up here I had, let's see, so A, B, C, and D. I have 4 different arrays. In each one of these, I only have 2 different arrays. So I'm in less danger of clobbering stuff. And remember we talked about you should shovel more and more calculations into that loop until you should stop. And when you get to too many, the compiler freaks out and throws its hand up and says, I give up, I don't know what to do now. And then you get terrible performance. So how do you know when to stop shoveling more calculations inside the loop? You don't. Exactly correct. Yes, you picked up on the pattern. There's no way to know, right? And it's so bad that not only does it depend on the hardware, the operating system, and the operating system version, and the compiler version, but a minor change to the compiler version, you put in the version that has 3 fewer bugs in it, could lead to major changes in where is the right place. So since you don't know, what should you do? Take a best guess, just like real life. Take a best guess. You can't know what the right answer is. You do the best you can. What is the probability that you will guess correctly? Lower. Anyone? So I'm going to give you an answer, then I'll modify it slightly. So the answer is 0%. You're guaranteed to be wrong. But it's an engineering 0%, not a mathematical 0%. It's not literally true that there's no way to accidentally get it right, but it might as well be true. It's close enough to the truth. Once in a great while, you'll accidentally do the right thing, but purely by dumb luck. And as soon as they change the compiler version or the operating system version, that's all gone. And heck, if tomorrow different people are running different kind of jobs on the machine, that may be gone too. There's no way to know. So you're always wrong in the long run, and you're almost always wrong in the short run. Okay, so we did that. All right, fission and fusion. So you cannot know whether you should fuse or fizz. There's no way to know. So you take your best guess. You can do some benchmarking, but remember that benchmarking information is very provisional, right? It's very temporary. It has a very brief shelf life. Inlining. And I think I'll wrap it up here. So look at this terrible thing. I'm calling this function 1,000,000 times. And calling a function, as we saw a couple of weeks ago, calling a function is very expensive. It takes time. I don't want to call this function 1,000,000 times. Now notice what this function does. Right? It doesn't do much. So if I can do inter-procedural optimization, if my compiler is smart enough to look at the thing that I'm calling and say, oh, I can do that. Look, I can just multiply this by 3. Boom. Now I've eliminated all those function calls. My code speeds up enormously. Of course, there's always a trade-off, isn't there? What if this function was 500 lines long? Now is it a good idea to inline it? We don't know yet. Maybe, maybe not. Who can say? Right? Especially, what if the 500 lines were 90% dead code? Maybe then it's a great idea. No way to know. Okay, we're going to wrap it up there. So we're already way over our time. But that should give you the general idea. And the purpose of today, I don't want to say was to frighten you, because that's not true. The purpose of today was to make you realists, to make you non-optimistic. Because if you are optimistic, you will often be disappointed. If you are a pessimist, and I say this from experience, you can be pleasantly surprised. If you're an optimist, you're usually disappointed. So be pessimistic about what the compiler will do, but also don't try and do too much for the compiler, because it might be better to let the compiler do that thing for you. It might know better than you, and it might not. It's a trade-off. Okay, and we'll leave it there. So thank you, everyone.